Hello, my name is Casey Shibler and I'm doing a reassessment video on electric field and charge distributions. I've chosen to do a couple of problems. So the first one is, suppose that the radius of a disk is r, which is equal to 20 centimeters, and the total charge distributed uniformly over the disk is q equals 6 times 10 to the negative 6 coulombs. Calculate the electric field 1 millimeter from the center and also 3 milliliters from the center, and does the field decrease significantly is the question. So I have drawn a figure. I have it going along the axis, and this is my radius r. So I have q, which is my charge, 6 times 10 to the negative 6 coulombs, my radius, which is 20 centimeters, which I converted to 0.2 meters, and for my equation I have the epsilon naught value 8.85 times 10 to the negative 12. So first it's asking to find the electric field 1 millimeter from the center of the disk. So I take my charge times my area, which is pi r squared, divided by 2 epsilon naught, times 1 minus the distance, which can be denoted sometimes as z, from the center, divided by the radius, which is 0.2. I get 2.684053 times 10 to the 6 newtons per coulomb. Then I have to calculate the electric field if it were 3 millimeters. So I do the same thing. I have my charge times divided by my area divided by 2 epsilon naught, and the following 2.657078 times 10 to the 6. As you can see, there is no significant decrease at all in charge. So therefore, I came to the conclusion that the field does not decrease significantly. Whenever I calculated in GlowScript, let's go to Edit Program, I calculated for the distance of 1 milliliter and 3, and as you can see, I got the answers, the first two. I then went on to calculate, well, I wanted to know how much would the electric field decrease if the distance increased even more. So I did it to 0.05 meters, as you can see here, instead of 0.003, and I get, let's see here, 2.02316 times 10 to the 6. So there's still not really a significant decrease. I then even went as far as to go to 0.1 to check to see how far it would decrease, and I got to 1.34877 times 10 to the 6, which is still pretty not too significant. My second problem is, let me find it really quick. Alrighty, if the magnitude of an electric field in air exceeds roughly 3 times 10 to the 6 newtons per coulomb, the air breaks down and a spark forms. So for a capacitor with a radius of 50 centimeters and a gap of 1 millimeter, what is the maximum charge that can be placed on the disk without a spark forming? And then calculate what strength the fringe field is just outside the capacitor. So let's see here. What I've done, I've drawn my capacitor with radius r and distance s. I have my electric field given, my s, my r, and my epsilon naught values. The electric field is equal to charge divided by the area divided by epsilon naught. So I plug that in and I get my charge. Then it wants to know what the fringe field is. So the fringe field is equal to the charge divided by the area divided by 2 epsilon naught times s, the distance between the capacitor, and r, the radius. So I then plug in those values and I get 3,000 newtons per coulomb for the electric field and the fringe field. I then went into GlowScript to check my answers, and, oh no. Let's see here. Right here is the point for, this is where I found the charge of the capacitor, and this is where I found the fringe field. So I go here, and I was correct. As you can see, 2.08 times 10 to the negative 5th and 3,000 newtons per coulomb. And this concludes my video.